Swayam Prabha. Digital India. Educated India.
Hello, good morning. So, welcome to the course on comprehensive view of speech processing, and today's lecture is 25th in series, and today we are going to discuss about vector quantization, and this topic we started in the last class, and today we will continue. And in the vector quantization, from the name itself, it is clear that here we are trying to quantize for the entire vector, not at the individual components of a vector. So, if you try to quantize the individual components of a vector, then it becomes a scalar quantization. So, that we have seen in the last class, like when you for example, if you have a speech signal in a time domain, and if you try to like represent a speech in a digitized manner, so we will first sample it, and afterwards each sample will be quantized with 16-bit samples. So, with that, the data rates that are required will be like around 160 kbps, right. So, that depends upon these data rates, basically depends upon the sampling rate and the quantization rate, how many bits that are used to represent a sample. So, almost like 160 kbps is required for representing the 1 second of a speech, if you try to represent the speech in a time domain or directly the raw samples. Suppose if you try to represent in a spectral representation, then we have observed that 16 kilobits per second is sufficient for representation of 1 second of a speech. So, that is because when you represent a speech in a spectral domain or in the form of spectral coefficients or spectral vectors, so we will try to split the speech signal in the forms of in a smaller frames or smaller segments of size 20 milliseconds or 30 milliseconds, and we will overlap these frames, and then we will shift the frames by 10 milliseconds. So, with that 1 second of a speech is represented by 100 frames, and again for every frame is represented by a spectral vector or some set of spectral coefficients. So, that way if you see that each spectral vector has 10 coefficients, for example, and each coefficient is represented by 16 bits. So, that way the total data rates that are required for representing 1 second of a speech will be like 16 kbps, because 100 frames and each frame is represented by one spectral vector which consists of 10 coefficients, and each coefficient will be coded by 16 bits. So, that gives you 16,000 bits per second or like 16 kbps. So, from time domain to spectral domain representation, we can see that there is a reduction of data rate of 10 times of order 10 when you represent the speech in a spectral domain. But as I mentioned that in a spectral representation, we are not representing the complete signal or a complex spectrum. We are representing only the magnitude spectrum. So, therefore, the recovery of the original speech may not be possible with the representation of only the magnitude part of the spectrum. So, then the other one is that in the vector quantization, here by knowing that the signal is a speech signal, and we know that it carries it consists of only some basic sound units or some set of sound units. So, for each language, in any language, if you see, the number of sound units will be approximately around 40 or maybe plus or minus 5. So, therefore, there are 40 sound units. So, therefore, each spectral vector will be one of the sound units, representation of one of the sound units. So, that way if you can able to code each spectral vector with like one of the sound units, there are about 40 sound units. So, for representing the 40 sounds, we need about 5 or 6 bits, right. So, therefore, each sound unit or each spectral vector is represented by the unique sound unit. So, it requires about 5 to 6 bits for representation of one spectral vector. So, there are about 100 spectral vectors corresponds to 100 frames in a second. So, that gives you about 500 bits or 600 bits per second is the requirement, if you can able to quantize with respect to whole vector in terms of the basic sounds, because we know that there are altogether around 40 basic sounds. So, these 40 can be represented by about 5 to 6 bits are good enough. So, that way we can able to represent the 1 second of a speech with 500 to 600 bits. And we know that here our speech has a lot of variability, because it's a physical produced from a physical system, and the characteristics of a physical system or a shape of the physical system and the movement of articulators, they are not determined, they are not fixed, right? They are varying, and that too the characteristics of a speech varying with respect to the speaker, and the sound unit characteristics also varies with respect to its context. So therefore, you need to allow some because there is some inherent variability in the characteristics of sound unit. So therefore, each sound unit, instead of representing by the only one representation, if you can able to represent, you can able to accommodate some variability, and that way suppose each sound unit, if you can able to view as some variants of around 25 variants. So that way the 40 sound units can be represented by like 1000 representations, because each sound unit, if you accommodate around 25, so 40 into 25, that becomes around 1000. So these 1000 representations can be encode with the 10 bits. So even if you that way, if you accommodate this variability also, you can able to represent 1 second of a speech with 1 kilobit per second, because there are 100 frames. Each frame is nothing but one spectral vector, and each spectral vector is represented by the 1000 representatives of the sound units, right. So that way we have 1 kilobits per second is required. And now to perform this vector quantization, in the last class we discussed about the basic elements of vector quantization as follows. So if you look at this block diagram, you can able to see that because for that means here whatever the spectral vectors are there, so all these spectral vectors are represented by some set of the vectors, representative vectors are known to be reference vectors, and all those reference vectors put together known to be code book. So here M is the size of a code book or the number of entries in a code book, and these code book vectors are also known to be the words, code words are also known to be code words, right, and are also known to be representative to spectral vectors and all. So because in the normal speech we have like infinite varieties of spectral vectors are possible, because as I mentioned earlier, because the sound unit itself, the characteristics of sound unit itself have a variability because of its positional where it is positioned, or because of its context, like what are the preceding and following sound units. So all those factors will influence on the characteristics of sound unit. So therefore there is an inherent variability of sound unit because of its context and position in a word or sentence and so on. And not only that, there are variability that is offered by the speaker, or the age of the speaker, and gender of the speaker, and the environment, and the device that you are capturing the signal. So all these things will play its role towards the variability of the sound units and all. So therefore we know that all this whatever the variability of spectral information, spectral vectors, but all of them are like they refers to only those 40 basic sounds. So to accommodate those variability, here we can say that each sound unit is represented by either 25 variations. It's not like the 25 is just I just picked up to leads to like 1000, altogether there is 1000 representations for that purpose. Otherwise in this 25 may have 100 and it may have 10 also even. So that way whatever the training data, that has to be represented with these 1000 vectors or these code book vectors. So for that what we do is that somehow we need to split these training vectors into groups, and the number of groups should be equal to the number of entries in a code book, and from each group we need to pick up one of the code vector or one of the representative vector, so which is like amicable or which is somewhat reasonably good enough. So that way here we can do it from the training data we can do clustering. So with the clustering is nothing but we will divide this entire training data into a different number of regions or different groups, and that can be done here. The number of vectors may be, for example, as I mentioned, like it may be million vectors or whatever. That means if you collect a speech from a different people or a different text and a different styles of speech, and different environments, different channels. All together, if you put like the data, the speech data that was collected will be around 10 hours or 20 hours or 40, 50 hours, for example. From that, if you can extract the spectral vectors with a shift of for every 10 milliseconds, if you can able to extract one feature vector, then that leads to about the lakhs or millions of spectral vectors that are available as a training data. And now we will try to divide this training data into groups, like that depending upon the code book size. So that way, if you for dividing that into groups, we can use some clustering algorithm, and the clustering algorithm will split that training data, whole data, into different groups, and from each group we will try to pick up or try to find out some representative vector, and that is known to be a code book entry or code word corresponds to that particular group. So that way we will form a code book or we will develop a code book. So once the code book is developed, then after that, for any speech signal which is produced, you can able to represent with the code book indices, because suppose for example, if a code book contains 1,000 representations or 1,000 code words, and now whatever the input speech, from the input speech you can able to derive the spectral vectors, and each spectral vector will compare with, will check with match against to all of the code book entries. We will get suppose there are 1,000 entries, we will get 1,000 distances, whatever the minimum distance that is there, given a code vector whichever offering a minimum distance. So that code vector, the index of that code vector can be given as the output. That means given a spectral vector, that will be encoded as the index of the code book. So that way each spectral vector is represented by the index. So for representing index, we use that 10 bits and all. And since we have 100 vectors per second, so therefore 1 kilobits per second is the data rate that can be coded or that can be used, that can be represented by using vector quantization technique. So now we will try to provide, we will try to discuss more about the individual elements of the vector quantization. That means these are the elements that are used for implementation of VQ. As I mentioned that in the case of training step, to prepare a code book to allow or to accommodate the variability of the spectral vectors. So we need to take a large set of spectral vectors like a V1, V2, V3 up to VL, where L is sufficiently large, right? And as I mentioned, like for example, you have a 10 hours of a speech, for example, right? And assume that how many spectral vectors are possible, because 1 hour means it's like 60 minutes, like 3600 seconds, right? So like for every second we have 100 frames, so it means per hour we have like how many 36,000 vectors are possible, right? So therefore since you have 10 hours, so it means 3,60,000. so that way you can able to see that depending on requirement you can collect the speech from different variabilities, right? And then you can able to, from that you can derive the code book out of it. Like so these are the spectral vectors. This L may be of range of like lakhs or millions or like billions, right? And then from this L we need to derive a code book of size M, and here the M may be either 1000 or it may be have like 100 or 200, whatever the size, that depending on your requirement. So this M is the size of the code book, and depending upon the size of the code book, so for representing each spectral vector we need to have like B bits are required, that is nothing but M we can approximate with a 2 power exponent. So whatever the exponent, that is indicating the number of bits that are required to represent the code book index or code book, each code word. And here as I mentioned that to get a sufficient or good representation of a code book, right, so the L should be sufficiently large, L should be much greater than M. So at least the L, that means the number of training vectors or the training in the training data, the number of spectral vectors required in the training stage will be like a 10 times that of the code book size. That is a minimum, that is the least at least that is the least size that is required for the given code book size. If the code book size equals to 1000, then the number of vectors in the training stage that is required will be at least like 10 times of that. That means 10,000 is required. It will be much higher number is good all the time. So this is the minimum the size of the training data that is required for the given code book size. Then afterwards, to perform the like to group these training data into the groups like M groups or M clusters. For that we need to find out, we need to make use of the similarity measure between the pair of spectral vectors. So with that we will try to find out the measure of by using a measure of similarity between a pairs of spectral vectors. So with that we will try to group the spectral vectors into the desired number of groups. Here in this case, if the code book size equals to M, we need to divide this training data into M groups. For that purpose we need to see that which of the spectral vectors are similar. So therefore accordingly we will try to divide the training data into groups, M groups. For that we need to have some similarity measure is required. So for that we use some distance metric, where here d of Va comma Vj, Va and Vj are the two vectors, two spectral vectors, and here this distance is nothing but it indicates the spectral distance Dij. So that means if the Dij equals to 0, it means that the Va and Vj are same, exactly same, Va and Vj, and if the distance is small, indicates that Va and Vj are very close, are very similar, very much similar, and if the distance is more, it indicates that Va and Vj are not at all similar, they are like they are dissimilar. So that way this distance measure will indicate the similarity between the pair of spectral vectors. And then the next thing is that we have to compute the centroid. We need to compute the centroid. That means after, by using this spectral similarity, we will try to divide that into group, and then from each group we need to compute the centroid. It is nothing but we have a group, like suppose for example from the training data, that will be divided into M groups. So from each group, like we need to find out the representative vector from the group, one representative vector from the group, and usually that can be picked up or that can be computed by using a centroid. Suppose we have a group of 50 vectors are there, and from that we need to pick up one of the like a vector or one vector as a representative of all 50 vectors. It means that that vector should be close to like the remaining 49 vectors. That is the way we have to pick up, or otherwise we need to find out the centroid, which is nothing but the mean vector. That means have 50 vectors are there, we will compute a mean across all the vectors, then we will get one mean vector, and that mean vector may not be present in the group of vectors. So that is an artificial vector, but that is close to like all the group members and all. So that way you can able to compute a centroid, right, and these centroids are happens to be your codebook vectors. That means from the L training vectors, the centroid computation is nothing but from L training vectors, using a distance measure we will try to divide that into M clusters, and then from each cluster we will try to pick up we will try to determine one representative vector. So that is a part of the codebook vector, that will be a codebook vector or known to be code word, right. So we have a M clusters, from each cluster will derive one vector as a representative vector. So that is your codebook entry. So that way we have M codebook vectors, and those are nothing but the centroids of M clusters. Then after that, once the codebook is ready, once the codebook is ready, finalized, then afterwards using a classification procedure we can able to represent the speech, unknown speech, or like the newly generated speech. Suppose you have newly recorded speech, from that you can able to derive by using the spectral analysis or by using FFT, you can able to derive the spectral coefficients for every frame. That means you will get a spectral vector, and then for this spectral vector we will try to match or represent this spectral vector using the code book. So how do you represent that using the code book? So the way is that whatever the arbitrary spectral vector, so that will be compared with all the entries of the code book, code words, then whichever the code book vector is closest to the arbitrary vector, so that index of that code book vector will be labeled, that is nothing but the nearest neighbor labeling and all. Using a nearest neighbor labeling, that is a concept. It means that this will be compared with all of them. So whichever is close to that, very close to that particular spectral vector, so that code book entry or that code word happens to be the representation of the arbitrary vector. It is nothing but we will represent this arbitrary spectral vector with the index of that particular code vector, right. So this is a way we will use the the VQ for representing the speech, right. So, first of all we need to collect some training data, and the sufficiently large training data which possesses all varieties of characteristics of a speech, like with respect to all possibilities, like with respect to speaker variability, with respect to language variability, with respect to environment, with respect to the sensors or the devices that are used to capture, with respect to different channels, right, and with all possible text to get the different positions and contextual information, all the possibilities to be provided as a training data. And from the training data, using this distance measure, you will compute the centroids, and those centroids happens to be your code book. And once the code book is ready, then by using a classification procedure you can able to represent the spectral vectors of a newly generated speech with the code book indices. So, that way you can able to represent the speech. Yeah. Now, we will see the details as I already mentioned here. The training data set should have these variabilities. The training data should have these variabilities. That means, it have like speaker variability. So, the speaker variability means the speakers of different age groups has to be participated in the training data, and that speakers have different accents, and the speakers with the genders, different genders, and the speakers with the different speaking rates, and the speakers which have with various the modulations, energy variations in the speech, and emotions, right, emotion levels. So, all these things, that means with respect to speaker, whatever the possible variations are there, all of them should be collected, right. And similarly, the speaking environments, it means when you collect the speech in a quiet room or in an automobile, that means when you are driving a car, that means the car noise also will be added to that, and a crowded places, like for example, have train stations and roads or market, busy market. So, where we have a lot of other noises also will be present. Babble noise, it means that suppose there is some party is going on, a lot of human crowd are there, and in that if you collect a speech along with the desired speaker's speech, there will be speech from other speakers also will be embedded or will be overlapped with that. So, it is known to be babble noise and all. So, likewise different speaking environments have to be covered, and different transducers and transmission systems. Transducers means the mic with the different types of mic and with the different types of devices. It means you need to collect the speech through your normal hand mic, and you need to collect the speech through a laptop, and you need to collect the speech through, for example, your mobile phones. Likewise, because there are different devices with which we are like using a speech as the interface. So, therefore, all sorts of that speech collected by different devices, right. And similarly, the speech that is transmitted through telephonic channel or wideband channels or narrowband channels, all of them, like the speech that is that is through different transducers and transmission systems. Transducers means the devices, recording devices and all, right. And the transmission systems means the way it is, like through the transmission is through like optical fiber or through a telephonic channel or through some other channel, like, because each channel has its own characteristics. So, when you propagate or when you transmit the speech signal through that, right. So, the characteristic of speech will be differed, the outcome of that. And likewise, the speech units is nothing but the text, what text you are using, right. It is like a conversation speech, right, and it is like isolated words, or it is like a digits, or like a passages, storybooks, like. So, all those things, all the different forms of text, and the different forms of speech, conversational speech, read speech, and different types of speech, all of them has to be part of the training data and all. So, because all these things will give you sufficient variability to represent the sound units in the code book. And then the dissimilarity measure or similarity measure, as I mentioned, similarity measure or a distance measure. So, this can be done by using this. So, this is the distance function d of Vi comma Vj, where Vi and Vj are the two spectral vectors, right, and the distance between them is denoted by Dij. It means if the Dij equals to 0 if Vi and Vi equals to Vj, and Dij is greater than 0 if Vi is not equals to Vj, right. It means that the distance should be 0, it means that both of them are same. Other than that, you should get some finite distance has to be there, right, it should be greater than 0. So, that way we have to use appropriate distance measures to find the similarity between the two spectral vectors, and right. And then for clustering the training vectors, the next thing is that we have a lot of training data that is available, which is collected from different variabilities, and now we need to, right, we need to group the training data. We have somehow from this training data we have to pick up like very fewer number of the representative vectors, and those representative vectors forms a code book, right. So, how to pick up a representative vectors from this huge training data, because as I mentioned that suppose if the training data consists of about 100 hours, then you have about more than a million vectors are there. So, from a million vectors you need to pick up only 1000 vectors as a representative or a reference code vectors which are part of a code book. So, how do we do that? So, for that we can able to somehow we have to split this 1 million or 1 billion vectors into groups, and the number of groups that are required will be as per the code book size. Suppose if you have code book, if you want to maintain the code book with 1000 entries, it means that all these 1 billion vectors, from that we need to pick up some 1000 representative vectors which are good in all respects. So, now how to pick up that, how do we derive these code book entries, or how to fill up, how do you develop a code book from the training data. So, for that here we are using a clustering process. So, using a clustering that means clustering the training vectors. So, it means that we are dividing the training vectors into groups, and from group we will pick up the representative vector as a centroid of a group or a center of a cluster and centroid of a cluster. So, for that here we are using a technique known to be like method known to be k-means clustering method, or it is also known to be generalized Lloyd's algorithm. Generalized Lloyd's algorithm, that means there is a Lloyd algorithm and it has different variations, and the generalized one is nothing but what we are going to discuss. There are some other variations of that, right, which gives you the clustering, but it is of different characteristics. So, here we are discussing about a k-means clustering, right. Here the objective of this k-means clustering is nothing but we have a L training vectors, that is L is nothing but very large set of training vectors, as I mentioned like 1 million or 1 billion, right. From these training vectors we need to derive m code book vectors, that is your objective, that is your objective of this k-means clustering algorithm or k-means clustering method. So, this k-means clustering method consists of 4 steps. So, the first step is known to be the initialization step. So, here, so first of all we know about how many code book entries, like what is the size of a code book, like what is m, m is 1000 or 500 or 2000 or 4000 whatever. So, what is this m? So, in the initialization step, so as per the m, as per the code book size, suppose if m equals to 1000, then we need to choose m vectors as initial set of code book words or code words of a code book, because we have 1 million entries, 1 million vectors are there, right. So, from these we need to derive only m vectors, right, which are happens to be finally they are the code book vectors. So, therefore, in initialization step what we do is that from this large training data, like that means 1 million vectors or whatever, from that we arbitrarily choose some m vectors randomly, we arbitrarily choose some m vectors randomly from this training data as the code book vectors. So, it means at the initialization step, at the very first step I prepared the code book consists of a code words, so which are very random, which are very arbitrary, right, which are very arbitrary, that means randomly we will pick up some m vectors from this training data, and those m vectors acts as a code book, the initial version of a code book, right. And but they are not proper because they are randomly picked up, but that random pickup may not be the optimal one. So, the second step is the nearest neighbor search, So, here we use the distance metric, right. So, the nearest neighbor search is nothing but like we have some initially we have some m vectors are there, right, where m vectors randomly we have picked up, and now for each spectral vector from the training data, right, from each vector in the training data, we will from this we will associate to one of the m code words, because there are m vectors that are arbitrarily chosen as the code words, right, and for each spectral vector we will associate to one of the m code words, one of the m code words of the current code book. So, at the initially the first at the beginning the code book contains the random vectors. So, what we do for each spectral vector in the training data, we will just take each of the spectral vector, and that spectral vector will be assigned to one of the code words, How do we do that? That is based on the spectral distance. Based on the spectral distance between that code word, that code vector, that spectral vector, and to the code word. So, we will associate each spectral vector to one of the code word. How do you do that? We will compute a distance. That means, for every spectral vector from the training data, we will compute the distance from that between that spectral vector and the code word. There are initially m code words are there. So, with respect to each code word, we will compute a distance from that spectral vector. So, we have that m distances are there, and out of that m distances, whichever gives the least distance, whichever is the least distance, then for that particular code word we will associate, or this spectral vector will be associated to that one. It is nothing but for that code word this spectral vector will be joined. So, that way for each code word the set will be grown, the set will be increased, right. Like for that way, suppose we have 1 million entries in the training data, we will take each of them and we will try to compute the distance between that vector and the code book entries, and then whichever the code book entry gives you the minimum distance, and then that particular that spectral vector will be offered or associated to that particular code book entry. So, that way by using nearest neighbor search, we will divide the entire training data into m regions or m sets, m regions, or you can say that m clusters and all, right, because each spectral vector will be picked up and that will be associated to one of the code words, that depending upon the distance and all. So, that way all the spectral vectors of a training data will be associated to one among those m. So, now if you take each code book entry, there are certain number of spectral vectors will be associated to that. So, all those spectral vectors together with that code book entry, that forms the like a region, or you can say that forms a kind of region or a group or a cluster. So, that way we will divide the entire training data into the m clusters, right, and then the next step is that centroid update. So, we have now divided the entire training data into m clusters, right, m groups, and now from each group we will pick up one representative vector. So, for that we use the concept of computing the centroid. So, therefore, from each group, like we will update the code word in the each cell using a centroid of the training vectors assigned to that, because here from the second step we are dividing the entire training data into m groups or m clusters, right. So, suppose for example, a cluster 1 contains of 400 vectors, right. A cluster 1 contains a 400 vectors, because in the 400 1 will be the random vector whatever we have picked up as a code word, and the 399 vectors are happens to be close to that particular code vector or that particular code word, right. So, now we have total 400 the vectors were there in that particular group, and computing a centroid is nothing but computing the mean vector, computing the mean of all those 400 vectors, that happens to be centroid, that happens to be the centroid of the particular group. So, that is one way to compute, and the other way is that nothing but from these 400 vectors we will try to pick up one representative vector which is close to all the remaining all vectors. The way it can be done is that we will take each vector and compute the distance of that vector with respect to remaining all 399 vectors. So, that way we will try to compute the distance of a vector with respect to remaining all vectors. So, that way we will do it for every vector, and whichever the vector has giving the specific vector is giving the minimum distance, and we will pick up and we will compute, we will say that this particular vector is the centroid of a vector and all, centroid of the cluster. So that way we can update the centroid for the group, for each group and all, for each group. So this is the centroid update. Then afterwards, once the centroids are computed, then what we do is that with respect to centroid, we will compute the distance associated to each group. That means we have, as I mentioned, that suppose a particular group has a 400 vectors, right? In that, one of them is the centroid. And now with respect to that centroid, we will try to compute the distance. We will try to compute the distance of the vectors that are present in that group, right. So it means that actually here we need to compute the average distance, that means we will compute the distance of that particular vector, all the vectors with respect to the centroid. Likewise, we will compute the distance for all the clusters and all. So we will get the total distance, we will get some total the distortion, because we are using these centroids as the codebook vectors, but there are several spectral vectors that are associated to that particular cluster. So we will try to find out for all those vectors what will be the distance, what will be the distortion, because whatever the vector is there, that all these vectors are represented by only one vector. So in that process, we will try to see that what will be the distortion associated to that particular group. Likewise, we will compute the distortion for all the groups, and then we will add up all of them. That gives you the total distortion, right, that is with respect to this set of centroids, So that way we will compute a centroid, and then we will perform the iteration. That means whatever, after you compute the distance and all in the first step, in the first iteration, then again you repeat the steps 2 and 3. So now in the steps 2 and 3, step 2 is nothing but now we have some centroids are there, because in the very first iteration, so those vectors are the very arbitrary random vectors. Now we computed the centroids, we updated the centroids, right, and now use those centroids as the representative vectors, and again perform the nearest neighbor search, and that means again take each spectral vector from a training data and try to see that where it is associated to, to which centroid it will be, which cluster it will be associated to. So that way now again all the spectral vectors of a training data, again we have to reassociate that. It means that again the groups have been formed, the new groups will be formed with respect to the new centroids, the updated centroids. So that way now the new groups have been formed. So for these new groups, again we will compute the centroids, right, we will again update the centroid. So we will get a new centroids. So with respect to these new centroids, again we will compute the distortion, is nothing but the total distance of all the groups with respect to the new centroids. So that way again, once you do that, we have to see that whether the distortion from the previous to this one, whether it has been decreasing or not. So it is decreasing, so therefore we have to keep on doing. That means we need to again use these new centroids, and then again perform the clustering, is nothing but again perform the nearest neighbor search, again divide into the new groups, and again the clusters will be, the centroids will be updated, and again with the newly updated centroids, again the distortion will be computed. So likewise here the 2-3 steps will be, the 2 and 3 steps will be repeated like successively, iteratively, until the distortion between the successive iterations is less than the threshold. It means that when you are iterating, so the distortion, because the centroids will be updated and the distortion will be coming down, will be decreasing and all, and after some iterations you don't see much change in the grouping and all. So therefore the centroids will be remain same. So therefore whatever the distortion that will be there in the successive iterations, they are like not much change, there is no significant change in the distortion, right, there is no decrement you can observe. So at that time, if the decrement is not significant, at that time you can stop the iterations, and at that time whatever the cluster centroids are there, those centroids happens to be the vector quantization codebook entries. So that way this k-means clustering here, first initially depending upon the size of the codebook, we will randomly pick up the vectors, and then we will update the groups, we will form the groups, we will derive the clusters, and the centroids will be computed and the distortion will be computed. Then again the new centroids are there. With the new centroids again will perform the clustering again, will that means using nearest neighbor search, and again the centroids will be computed, then again. So this way this process will be repeated till the distortion is not coming down, or distortion is more or less remains same in the successive iterations. So at that time whatever the cluster centers are there, there happens to be the code book entries. So this is known to be a very well known k-means clustering approach, with which the training data will be splitted into groups, and from the groups we will derive the centroids, and those centroids that happens to be the vector code book entries and all. So this is pictorially you can able to see the way the clustering will be happening like this. So like initially here we just pick up some vectors, and then the code book, all the training data will be find out the distance with respect to each of the centroid, each of these vectors, and then whichever is close to that. So that way here the spectral vectors that are there within this region are associated to this one, and the spectral vectors associated to this region are have been associated to this one. So likewise the groups will be formed automatically. The number of groups will be that depending upon the code book entries. So this way the groups will be formed, and from this group we will compute the centroid as a mean vector, or as the one of the vectors which is close to all the vectors, which gives the least distance to all the vectors. So that vector has been chosen as a centroid. So that way you can able to see that the regions will be formed, and from the region the clusters, the centroids will be carried out. And here if you look at the feature vectors, like, and if you downsize the feature vectors to only 2 dimensions, then you can able to see that how the centroids will be spread in the whole data. You can see this one, and then afterwards the centroids will be moved away from that. This is the, suppose if your spectral vectors of 10 dimension, you cannot visualize this, the formation of centroids, right, in a 10 dimensional space. So therefore if you want to visualize that, you can downsize that spectral vector size from multi-dimensional to the 2-dimensional, where you can able to, now you can able to represent that how these the spectral vectors are spread over in the 2-dimensional plane, and from that you can able to see that what are the centroids, how they are, like how the spread will be, and all these things you can able to observe in a lower dimension case. So this is just to represent that, just to show that, to illustrate or to demonstrate that the k-means clustering, how the regions will be formed, and how the centroids will be derived, and then in the 2-dimensional plane you can able to see how the data will be spread and what will be the centroids. So this way you can able to see, and here you can see that all the centroids are spread across the entire data. So therefore this is a reasonably good clustering and all. Otherwise, suppose if all these points are somewhere here very close density, it means that the approximation is not good, or the clustering process is not good. So but in the k-means clustering it is computationally intensive, because you see that at the beginning itself we are picking up m arbitrary vectors, that means m centroids we are picking up as arbitrary vectors, and each vector in the training data you have to compare with, or you have to find out the similarity with respect to all these m vectors, and then it has to be associated to one of the vectors. So that way the nearest neighborhood search is a lot of computation that is involved with the k-means clustering, because from the first iteration onwards each vector of a training data has to be compared with the m vectors, m arbitrary vectors or m centroids and all, and this has to be carried out in each iteration and all. So think about, suppose for example your training data is of order of 10 power 9, right, and the code book size equals to 1000, then you see that how many comparisons are required in each iteration. So it is very computationally intensive, right. So instead we have some other approaches, some other methods which are suboptimal, which may not be optimal, but that also gives you some reasonable number of clustering, and reasonable accurate clustering can be possible. And one of them is the vector quantization using binary split algorithm. Binary split algorithm. Here the binary split algorithm, the process will be something like this. So here what we do is that from the first we will collect the training data, covering all variabilities. Then afterwards, so first what we do is that in initial step we will start the code book size with one vector. We will start the vector code book or vector quantization code book, right, with only one vector. So if we want to pick up only one representative vector from a 1 million vectors or one or like whatever billion vector, it is a simple. That means you need to calculate one vector which is close to all the vectors, So it is nothing but simply computing a mean vector. If you compute a mean vector, so that mean is nothing but the mean vector is nothing but it will be close to somewhere around the center of the entire training data. So that can be treated as a representative vector. So the code book size of one vector is nothing but computing a mean vector, right. And after that what we do is that here the code book size will be doubled in each iteration. The code book size will be doubled in each iteration till you reach the whatever the size you require. Suppose you require the 1000, right, 1000 is our code book size if we want. Then first you start with 1, then you double it, it becomes 2 vectors, then again you double it, then it becomes 4 vectors, then like 8, then 16. So likewise you keep on double the code book size until you reach the sufficient size. Suppose if you want to have 1000 is required, then in the process you reach the code book size size will be 1024, because 10 times if you double it successively you can reach the code book size will be 1024. That is good enough for your 1000 code book size. So here the way we double the code book size will be the following way. First we start with a one vector code book, and then afterwards then we will double the code book size by splitting the code book entries as, suppose your y of n is your code book entry, for example one of the code book entry, right, and when code book size equals to 1, then this is only 1, is nothing but y1. So this y1 can be split into 2 vectors. Y1 will be split into 2 vectors. How do we do that? So the one of the vectors will be yn into 1 plus epsilon, and the other vector will be yn into 1 minus epsilon. Here there is a mistake. Here is a 1. This 1 minus epsilon multiplied by yn into 1 minus epsilon. Here yn plus is nothing but yn into 1 plus epsilon, right, and yn minus is nothing but yn into 1 minus epsilon. So that way we can split the code book size of 1 into code book size of 2. Now these are the two representative vectors, and again you apply a k-means clustering. You apply the k-means clustering on the whole training data by keeping these two as the representative vectors, right. It is nothing but now you started your k-means clustering with k equals to 2, and now these are the two arbitrary vectors. And now you apply a k-means clustering on these, and you try to find out which are the best the code book with the 2 entries, right. And after that, what you do, use the k-means clustering algorithm to find the best set of centroids for the given size 2, and now you iterate the steps 2 and 3, because the 2 is not good enough. You want the code book size of 1000. So therefore in the first iteration you are doubling the code book from 1 to 2, and in the next iteration you are making that again you have 2 entries are there. For each entry again you make it double, like the same process. So that way then the second iteration your code book will be increased to 4, right. Each iteration you are performing the k-means clustering, because now here first initially you are taking the 2 vectors as a code book entries, and then you apply k-means clustering and you will get the efficient those 2 vectors, and now again you are splitting those 2 vectors to 4, right, and now by applying k-means clustering you will get a 4 centroids. So likewise you keep on splitting the code book entries to double, and then apply a k-means clustering to get the efficient centroids. So that way you can instead of in the normal k-means clustering we will start from beginning itself, we will take a k vectors and then keep on refining, and then the clusters will be updated in each iteration. But here the beginning you start with one vector, then you double it, and so on. Likewise after some stages iterations you will get the code book of desired size and all, then you can stop it, then you may stop it. So this is known to be a binary split algorithm, but this is somewhat computationally efficient compared to the normal k-means clustering, because as you can see intuitively also the number of comparisons or number of computations that are required will be not as high as the k-means clustering, right. So, this is the flow chart corresponds to the binary split algorithm. As you can see here, whatever I just mentioned here, this is pictorially represented over here and all. And here also we have to, that means here the binary split algorithm, but inside that we are using k-means clustering, but the k is varying. Initially it will be like a 2, then afterwards it will be 4, then it will be like 8, then 16. So, that way we are gradually increasing the code book size to a desired size, and this way you can able to, this is one way to like develop a code book like using a binary split algorithm with slightly less computational. And so, if you want to see that which one is more accurate and all, so that you can able to verify that by evaluating the code books. And now, if you look at this, suppose for example, if you have a code book size, we know that the number of words, the number of sound units will be 40 maximum, right. So, therefore, here by using the binary split algorithm, suppose if you develop a code book of size 32 for example, of size 32 slightly lower than 40, right, because we know that number of sounds will be only 40. So, therefore, if you try to represent the spectral vectors like with only the unique representations. So, the 32 size code book, if you look at, if you try to prepare a 32 size code book, vector VQ code book, then and those code vectors, like whatever the code book entries, there are each of them are 10 dimensional vector, but actually as I mentioned earlier, we cannot visualize that in a 10 dimensional space. So, therefore, from these code vectors, what we can do is that from this we will try to find out the F1 and F2, because we know that from the spectral vector you can come to know that what is F1 and F2. So, if you can able to derive F1 F2 from each of the code vector of the vector quantization code book, and then if you plot them in this F1 F2 plane, you can able to see that these dots or whatever the black circles, filled circles, so they are the vectors, these are the 32 vectors whatever is over here, right. It means what here the observation is that if you make the code book size is smaller, then all the entries of a code book size, they are like mostly concentrated at the center of the plane. But in reality, as we have seen earlier, when because the sound units having the variability, so when you observe these the vowels, when you plot the spectral vectors of the vowels in the F1 F2 plane, right, for the vowels, this is the observation, these ellipses whatever is there here, this corresponds to E, and this is the long E, this is A, and this is woo, this is oo. So, but here so that way you can see there is a variation, the spectral vectors are spread across this entire ellipse. Now, using a vector quantization with a 32 size code book, if you analyze the spectral vectors, because because those vectors, the code book entries, they corresponds to different sound units, right, they corresponds to different sound units. But here when you try to plot in F1 F2 plane, so they are observed to be, all of them are like observed to be around oo, around the some common vowel oo kind of a thing. It means that here the vector quantization of size 32 code book is not performing well, because it is not giving enough variability at all, because all the vectors are just focused or mostly concentrated or mostly spread at the center, at the some average vowel or something like some common vowel like oo kind of a thing, right, but the spread is not there. So, therefore, from this the observation is that if you take a code book, if you consider a code book of very small size without accommodating the variability, then what you observe here is that the performance is not good, the performance, because otherwise actually if it is performing well, then these dots they should spread over, that indicates the variability. But here now all the dots are very close proximity, they approximately represents the a few vowels only, but actually we have about 40 vowels, 40 sound units, but they are not representing that, because the reason is that since we are not accommodating any variability, so therefore all the VQ entries, they are observed to be very close, and so this is not a right representation of the spectral speech with a code book size of 32 and all. So that is what the observation, but here if we increase the code book size, then these dots whatever is there, we have several dots will be there, and those dots will be spread over the entire F1 F2 plane. So that is a good representation, right. So this one, from this the observation here is that this cannot be used, or this cannot be sufficient for representation of the code book size of 32 is not good enough or not sufficient to represent the speech. And here is one more thing from the code book, like if you try to compute the distortion, here how do you compute the distortion? From a training data you can able to compute a distortion with respect to code book, right. Code book is nothing but centroids, right. So the k-means clustering algorithm or a binary split algorithm, all of them are developed by computing the distortion with respect to the updated centroids, and then if the distortion is not changing much from the successive iteration, then we will stop, right. So here if you analyze the distortion for code book of different sizes, here the code book, instead of the size of the code book, instead of mentioning directly, here the number of bits that are indicating the index, code book index has been given. So what it means here is that here when you choose 6 means the code book size of 2 power 6, and 10 means the code book size of 2 power 10, something like that. So therefore if you analyze the distortion with respect to the code book size, you can see that when the code book size is very small, right, with the 2 vectors, 4 vectors and then 2 power 3 vectors, the distortion is very high, and then as the code book size increases, right, as the code book size increases, the distortion will be drastically reduced. You can see the slope of this is decreasing very rapidly, right. So you can see that like there is a drastic decrease in the distortion, right, from the increase in the code book from very smaller values to the moderate values and so on. But after that you can see if it is a beyond 10, like 2 power 10, the code book size of beyond 2 power 10, then there is a still decrease in the distortion, but the decrement in the distortion is not that significant and all. So therefore this observation valid for both voiced and unvoiced speech segments. That means the spectral vectors corresponds to voiced segments and spectral vector corresponds to unvoiced segments. For both of them the same observation is noted. So what it means is that the code book size or the size of a code book should be reasonably large enough so that the distortion will be less. That means the distortion means the actual distance between the actual spectral vectors to the code book entries. So that is the distortion. So the distortion will be come down or reducing as the code book size increases, right. So this is another observation, like which is the trade-offs between the code book size versus the distortion and all. Like as the code book size increases, the distortion will come down, but at the same time as the code book size increases, then the memory required to store the code book also increases. That is again another constraint. Okay, we will stop here at this point. In the next class we will continue the other aspects of the vector quantization. Okay, thank you.